Yeah, so in case of discrete basis, that means in case of psi n, suppose in case of particle in a harmonic oscillator or particle in 1D box, am I right? The most general state is written like this, am I right? So x comma 0 or x comma t, isn't it? So that's equal to summation over Cn into psi n, because it was discrete basis, isn't it? Yeah. So and again psi of x comma t, we could have written summation over n Cn psi n Cn e power, why it is not showing off, e power minus I En t by h bar, isn't it? We have seen all of this. Now, in case of continuous basis, again, these were individually normalizable, okay? And we have observed them, okay? In case of continuous basis, what was our continuous basis? Psi k, isn't it? Of x is equal to e power ikx, am I right? This was our continuous basis. Or you can write ikx minus omega t also. Suppose if you want to write the time dependent function, isn't it? Psi of x comma t, but we put label k. Why? Again, it's a continuous basis. We put label n because it is a discrete basis. It depends on integer. Am I right? We have already discussed this one. And since k is continuous, again, since n is discrete, we have made the summation here. Since k is continuous, what we have done here is we made the integration of e power I kx minus omega t dk, integral over dk, because here it is summation over n is a variable here. Here k, again, each of these state is what you call defined by k. So integration over dk, coefficient depends on n, coefficient should depends on k. We call that as pi of k, isn't it? Minus infinity to plus infinity. To make formula comfortable, we put 1 by root 2 phi, isn't it? We have written the most general solution, am I right? Can I write this one as gs? So similarly, this one as most general solution is written like this. And this kind of solution is normalizable. And you have seen this solution, this is similar to superposition state in case of our discrete basis. It contains many what you call k values or many what you call momentum values, because p is equal to h bar into k, isn't it? You can write like that. Now look at here. What does mod Cn square says here? Okay, in this case, what does mod Cn square says? Mod Cn square is probability of getting En. Am I right? Mod Cn square is probability of getting En. Similarly, this coefficient, but this coefficient is continuous now. This coefficient, it was discrete. Am I right? C depends on n, but pi of k, isn't it? This is very continuous function of k. So that's why again this pi of k, mod pi of k whole square into dk. So that is probability of finding the k value between k to k plus dk. Can you find the similarity between these two? Here also it is coefficient, here also it is coefficient, but it is continuous basis. So this variable is continuous here. This coefficient is continuous function of k, and mod square will give probability density. Actually, mod square into dk, it will give probability of finding the particle whose k value k to k plus dk, where it's what you call momentum is p is equal to h bar into k. Okay, so can you find the similarity? Wait a second. To make the formula comfortable, what I do here is I'll use Jatili symbol, because rather than writing in this way, yeah, okay. If you write in this way, what is psi of x comma 0? 1 by root 2 phi integral minus infinity to plus infinity. You can write phi of k into e power I kx into dk, isn't it? So now this pi of k, it is our Fourier transform. Okay, if you see this one as Fourier transform, then phi of k should be inverse transform. Am I right? 2 pi integral minus infinity plus infinity psi of x comma 0. Okay, psi of x comma 0 into e power minus I kx into dx here. Okay, I hope we have seen all of this, isn't it? This coefficient is a inverse transformation. So this psi of x seems to be Fourier transformation of phi of k. Okay, and phi of k is a inverse transformation. You can say like that. Is that okay? And just I put t equal to 0 here. If I put t equal to 0, this omega t part is not there here. Okay, that's the only change. So now we call this one as what you call momentum space wave function. This one as position space wave function. So wait a second, I'll talk about that. So rather than writing in terms of k, I'll directly write in terms of momentum. Okay, just like in Jetili. Yeah, let me write in terms of momentum here. Look at here. Psi of x comma t is equal to 1 by root of 2 pi h bar. Okay, 1 by root of 2 pi h bar. Again, I have sent very clear message. Don't join if you are too late, isn't it? Minus infinity to plus infinity. Okay, phi of p into e power I. What I do here is I'm going to what you call I'm going to manage h bar here. H bar p is equal to h bar k. Somehow I will manage that h bar here. E power I uh, p by h bar x minus e by h bar t into dp. So it's just from this equation. Look at here, we have taken h bar here, and again what we have done is we have taken one of the root h bar along with phi of k. Actually, okay, why this root came here? Actually, 1 by h bar should came here, but root came here because one of the h bar we are going to keep it along with phi of p. You will see that one. Okay, so again e by h bar is omega. That's what we have written earlier. Okay, e by h bar is equal to omega. Okay, or e is equal to h bar omega. That's what we have written earlier. Okay, e is equal to h bar omega. Okay, I hope you can see all of this. Now in this one, so phi of, again, so psi of x comma 0. How do you write? 1 by root of 2 pi h bar, 1 by root of 2 pi h bar integral minus infinity to plus infinity phi of p into e power I p by h bar into x dp. So now phi of p is equal to 1 by root of 2 pi h bar into integral minus infinity plus infinity. This one, am I right? Psi of x comma 0 inverse transformation e power minus I p x by h bar into dx here. Okay, so this is the best way to define them. Okay, in terms of momentum. Now look at here. Again, what does this coefficient says? Mod phi of p the whole square into dp. This is probability of finding the momentum. Okay, probability of finding the momentum of the particle from p to p plus dp. So here Cn square was probability of finding the energy. So here mod psi of x comma 0 the whole square or x comma t the whole square into dx. What was this one? Probability of finding the position of the particle from x to x plus dx. Okay, so similarly, so this mod square, this coefficient mod square, just what you call compare this one with the psi of x comma 0 is equal to summation over cn into psi n, where mod cn square is probability of getting en in this very similar manner. So again, just see this one as a linear combination. So this mod square, but it's a continuous function. You should put dp here. So only this part is dimensionless. Okay, mod pi the whole square, it will have some dimension. Okay, into dp. That's the probability of finding the momentum of the particle. Okay, I'm not writing any sentence here, I'm writing in this way. Is that okay? So anyone reply quickly. So that's why we call this as momentum space wave function. Okay, we shall discuss about this one later. Okay.
Yeah, in modulus 5k square dk, we are getting what probability means k means.
Yeah, probability of finding k of the particle, where h bar k is what you call your momentum. You got to say like that, or you can call it as k as a wave vector, where k is equal to 2 pi by lambda, where lambda is a de Broglie wavelength of a particle, because we are talking about particle here. That's very important. So can you hear me? Any problem?
So observing the momentum of.
Hmm. So again, yeah, this will give the probability when you do the measurement of momentum, when you do momentum measurement. Okay, we call this as momentum probability density. This was position probability density, isn't it? Psi of x comma 0 whole square, or psi of x comma t whole square. This was position probability density, isn't it? So similarly, phi of p whole square. This is momentum probability density. Is that okay? Speak up. Yeah. Now, again, we can understand lots of things here. I mean, about uncertainty. Now, look at here. We got the information about position as well as what you call momentum. Information is only probabilistic information. Okay, that's the best thing we can do in quantum mechanics. Okay, so now let me go for example number 2.6. Okay, example number 2.6. Okay, let me first define the example, then I'll show you the animations that I have done. Okay, so psi of x comma 0, free particle. Okay, we are talking about a free particle with initially it is localized, actually that's what he said. So that's equal to capital A when x is between minus a to plus a. Is that okay? It's equal to 0 otherwise. Okay, when you normalize, so can I write directly? Again, you have to normalize this one. Mod psi x comma 0 whole square minus infinity to plus infinity dx is equal to 1, but this will be mod a square integral minus a to plus a dx is equal to 1. What is a? 1 by root 2a. Is that okay? Can you do this normalization as earlier? Let me write it very directly. Is that okay? Speak out, anyone.
Yes, sir.
Yeah, any question? Let me write, this is the normalized wave function, 1 by root 2a. Okay, so now you have to find momentum space wave function, or pi of k, or you can call it as a coefficient in its expansion, in the expansion of this one. This is equal to 1 by root 2 pi 1 by root 2a integral minus infinity to plus infinity, or minus infinity to plus infinity, that will be converted into minus a to plus a. Why? This is 0 outside. Okay, but actual integral is minus infinity to plus infinity into e power minus I kx into dx. Am I right? I have just used other definition. Okay, just check that out. I think I have given this one, isn't it, in the last class itself. Let me write my last answer directly. Okay, solve this one. 1 by root pi a into sine ka divided by k. Okay, what I feel comfortable is, okay, this one. I'm going to multiply and divide by a. I need a here somehow. Multiply and divide by a. This will become root of a by pi. Can I write like this? Sine ka divided by sine ka divided by ka. So this is my pi of k. This is my psi of x. Okay. Now, so try to plot them as he has drawn. Okay. He has already drawn them. Okay. But I'll use GeoGebra here. But you should try to draw that one by hand. Is that okay? So can you try? Is that okay? So now let me take what you call wave function. Okay. So can you see these plots?
Yes, sir.
Now look at here. So what I made here is I made a what you call, so a can be changed here. Okay, I don't know how to do in a touch screen. Yeah. Now let me keep a value some moderate here. Okay, a equal to 5. I put a equal to 5 here. Okay, so this what you call blue curve. Can you see this blue curve?
Yes, sir.
Yeah, this blue curve minus a to plus a. Okay, it is 0 outside. So this is psi of x comma 0. Okay, so this is momentum space wave function, root of a by 5 sine a k divided by a k, or sine k a divided by k a. Okay, so this is red curve. Red curve is momentum space wave function. Blue curve is position space wave function. Okay, so now look at here. If you want to have very well defined position, look at here how uncertainty will be there as an inbuilt phenomenon. Okay, if you want to have what you call well-defined position. Well-defined position means psi of x should be very narrow. Am I right? Isn't it? If you want to have psi of x very narrow, so can I look at here? I'm trying to make this psi of x very narrow. Can you see this part? Psi of x 0 outside this one. Is that okay? Psi of x is between minus 0.3 to plus 0.3. Okay. I mean, my again in this situation, so in this state, my particle is somewhere here. Okay, in the very short region. So can I say like this? Hmm? So now in that situation, look at here, what is the momentum of the particle? You can write in terms of
Sir,
phi of p.
sir,
Yes, speak out.
I didn't get it.
Yes,
I didn't get that part.
which part?
That you are saying minus 3 to plus 3, you said something
No, no, no. Again,
near that
I put
only.
a equal to 0.3, isn't it? So it will be between minus 0.3 to plus 0.3. Minus a to plus a, 1 by root 2. Okay. So that means what I'm saying
But the
is,
graph is not showing that it will be between.
no, no, again, there is no what you call lines here actually in this graph. Okay. So this is this one. Can you see this one?
Yes, sir.
Constant. This is a constant. It is 0 outside actually. Is that okay? So can you
Okay.
see this one?
So,
Is it okay? It is 0 outside. So it is non-zero. I mean, so this has a very well-defined position. Am I right? I made a very small, a kind of localized particle. Localized means, so it is a kind of what do you call? It is there only in this region. I can say like that. When you try to make that position well-defined, little bit well-defined position, so then what will happen to what you call your momentum? Look at here. It will be widely spread, isn't it? Your red curve, that is your momentum space curve. Again, k, again you can so here this x-axis is k. Okay, for red curve x-axis is k, for blue curve x-axis is x itself. Okay, yeah. So now look at here, k is nothing but momentum. Can I say like this? Because h bar k is p. Okay, so that's why again if you make what you call position distribution very narrow, this is a narrow distribution. Okay, so there is no line here. When you make this position distribution narrow, that means it is 0 here, it is a very high value here. Okay, so corresponding momentum distribution will be widespread, isn't it? Are you getting my point? This is an inbuilt uncertainty, you don't have control over it. Look at here, if you want to make momentum distribution narrow, hmm, then what will happen? Position distribution will have more uncertainty. Uncertain, can I say like this? So our position becomes more and more uncertain. So can I say like this? If I want to make momentum certain, I mean, now I know that again my momentum value is somewhere here, isn't it? Again, it is very less here, isn't it? That let me take mod psi square. Is that okay? Let me take mod psi square here. Yeah, this is the best idea, isn't it? Isn't it? So now if I want to have very well defined position, if I want to have very well defined position here, okay, so this is my mod psi square. Okay, so can you see this one?
Yes, sir.
Yeah, so this is mod psi square. If again when I make this a small, A small means again particle is what you call so somewhere here, okay, in the small region. So again this is my distribution, okay. Mod psi square is a distribution. Earlier whatever I have drawn, this was the wave functions actually. Hmm? So these were wave functions, what you call psi and phi. Here I have drawn mod square of them, okay, because mod square will talk about probability density, isn't it? Now look at the distribution, position probability distribution. Can I say like this? This what you call blue curve is a position probability distribution, which has very less uncertainty. Am I right? Can I say like this? Because I know position, where is the particle between this region, less uncertain. Am I right? So then, what is the momentum? It is very widespread, more uncertain. Isn't it? If you do the measurement, you make it here, 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 or here, isn't it? If you take identically prepared system, all are prepared in the same state, your what you call momentum measurement will have very wide range, or momentum uncertainty is more. And if you want to make momentum uncertainty less, a large, okay. If you want to make momentum uncertainty less, you should make a large. Is that okay? You should make a large. If you make a large, what will happen? Yeah, your momentum probability distribution is a spike, isn't it? Mod pi k square. That means you know what is the what you call momentum of the particle. It is somewhere here, isn't it? But your position, what you call, is very uncertain. Can you see this graph? This is parallel to x-axis, just above. It is very widespread, and you don't have control over it. Now, can you say I'll make more again? I'll make a state where both position as well as what you call momentum is more accurate. That's what we always think, am I right? Whenever we see uncertainty principle, what we think, I'll try to make some arrangement, experimental arrangement, so that I can measure position and momentum simultaneously and precisely, isn't it? No, it is not like that. It's an inbuilt phenomena. If you try to prepare a state with well-defined position, momentum will be ill-defined. If you try to prepare a state in this case, okay, with well-defined momentum, it's a well-defined what you call momentum state, your position will be ill-defined. Yeah. Hmm. Hmm. Yeah.
Sure.
Yes, speak out. Wait a second. No, no, this blue graph, so because A is larger here, okay, it is close to x-axis because total area under the curve should be 1, am I right? We have normalized it now. So it is close to x-axis. When you zoom in, you can see that one, okay? It is parallel to x-axis, but look at here. What is the probability of finding the particle? It is between minus infinity to plus infinity, isn't it? Pick out. So and your red graph again, your mod pi k square, it is becoming narrower and narrower. Yeah, again it will be almost spike actually. We can't see its height actually. Is that okay? Speak out. Yes, speak out. Somebody was asking some question. I'll make it
Sir,
quiet.
we are getting uncertainty in momentum here.
Hmm.
So these wave functions are not eigenstate of momentum either.
No, no, no. Okay, these are not eigenstate of momentum. Look at here. This was eigenstate of momentum. Which one? Psi k. Hmm? X comma t is equal to a e power I kx minus omega t. Okay. This was what you call, if you operate p cap on this psi k, you will get h bar k into psi k. Okay. This was the what you call definite momentum state. Now whatever we have designed here, this one, this is not definite momentum state. This is composed of range of momentum, continuous range of momentum. That's what I was trying to argue. Is that okay? But look at how mathematics works here. Okay. If you want to have well-defined position, your momentum will be ill-defined. If you want to have well-defined momentum, your position will be ill-defined. You don't have control over it. This is uncertainty. Is that okay? Speak out. Any question?
So it's totally separate from discrete basis.
Yeah. Again, in discrete basis also you have uncertainty in the measurement of energy. Am I right? when you have linear combination, right? You can't say which energy it is, but here you have uncertainty in the measurement of momentum. When you see the linear combination state itself, okay, when you see this state itself, you should say, yeah, you can't say which momentum it is, isn't it? Because it's a combination of many momentum, continuous range of momentum, in fact, isn't it?
What about energy here?
No, again, we don't what you call go for energy measurement. Energy measurement, you can say like this: E is equal to P square by 2m. If you measure P, okay, you can take square by 2m, and you can talk about energy measurement. Hmm? The again, because again, so here also you can talk about only some range of energy. You can't talk about exact energy because it's not discrete. There is no discreteness of energy here. Is that okay? Yeah. So that's why this will help us. Again, look at here. What helped us here is this helped us to understand uncertainty principle here. It's not about measuring apparatus, isn't it? It's about preparing a state. You can't prepare a state with well-defined both position as well as momentum, isn't it? And this is the best example. Okay. So let us see some mathematics here. Okay. So this sine Ka divided by Ka, isn't it? Pi of K sine Ka divided by Ka root of A by pi, isn't it? So now, when this A is very small, okay, so Ka is also small, isn't it? When A is very small, K is very small. In that case, pi K. I mean, if you want to plot that one without any graph or something, okay, you should be able to do that one. Pi K is nearly equal to root of A by pi sine theta by theta. When theta is very small, nearly equal to 1. So that this is nearly a constant. That's what I was to show here. Okay. So when A is very small here, what happens? When A is very small here, okay, what will happen is your pi of K, okay. So nearby again, when K is very large, then sine theta is going to play the role. Okay. So this is nearly a constant. Okay. So try to plot this one. So try to plot again with a different approximation. Is that okay? The exercise here is, so again take A small and try to plot this pi of K. Okay. Take A large, then try to plot pi of K. Is that okay? So that's why. So when A is very small, okay. When I made A very small, okay. Here I made A very small, around 0.3 here. Can you see this one? Can you see this 0.3 here on smartphone?
Yes,
Yes.
sir.
Yeah. So now then this will become almost constant. Okay. This your pi of K becomes almost constant. Here you can talk about mathematics here, isn't it? But this one, when A is very small, sine theta by theta, theta is very small. That's nearly equal to 1. That's why it is root of A by 5. Since A is very small, height of the graph is low, isn't it? Figure out. Hmm? So similarly, when A is very large, so then what would happen? This is mod square. When A is very large, then what will happen? So this, if A is very large, hmm, so then your psi of x comma 0, that's equal to 1 by root 2a. Am I right? X is between minus a to plus a, isn't it? 0 otherwise. So when a is very large, this height of psi x comma 0 is low, but it is very wide. Yeah, wait a second. Height is very low, but it is widespread. So since A is very large, what will happen is sine curve will touch 0 again more frequently. Can I say like this? So pi of k is equal to sine ka divided by ka, isn't it? So this ka, since a is large, okay. For short value of k, what will happen? Again, sine 2 pi will come quickly, isn't it? When a is very large, root of a by pi. Okay, that's why it's going to touch 0 very frequently. Hmm? So that's what you can see here. Is that okay? Yeah. Again, this is mod square of those curve. Okay. Yeah.
So,
Speak out. Any question? Yeah.
so all those graphs, I mean, it plays right in A.
Yeah, definitely. Again, I made a variable here because a will decide the what you call position uncertainty here. Am I right? Ah,
It is saying that minus a
ah.
x variable. That means what's showing in this graph.
No, no. So again, in this graph, that means you can find the particle between this region. That's the meaning of that one, isn't it?
X means
Yeah, x means position only here. Yeah, speak out. Any question?
so when I squeeze the region of interest,
Yeah.
then
Then what will happen?
then this
Hmm.
momentum will define it.
Yeah. Again, I can't make it 0. No, no. When I squeeze A means I made position more uncertain here, isn't it?
Certain.
Huh? What you call your momentum will be more uncertain. You can see that. Yeah. So let me share this one. If you have piece, you can play with that one. Okay. Yeah. So this is the basic inbuilt uncertainty principle. And whenever you try to prepare a state with well-defined position, your momentum will be ill-defined. Whenever you wish to prepare a state with well-defined momentum, your position will be ill-defined.
So how do we plot this graph in GeoGebra?
No, no, again, that you better not to take care right now. You better take care about book plotting graph by hand. Okay. Later you better learn. Is that okay? Not right now. Right now, don't think about plotting like this in GeoGebra. Okay. It's quite easy. It's not a big deal. Okay. You can search in YouTube. You'll get lot of what you call tutorial videos. You can plot this one. Not a big deal. Is that okay? And Python is the best language to do this kind of interactive what you call graphs. But I need to learn Python. Okay. So that's a different story. Okay, right now try to understand this one. I'll share this one. You just play with your PC if you have PC. Okay.